Hi, in the last video, we discussed about how do we handle or how do we perform a simple linear regression or multiple linear regression if one of the independent variable is categorical, right? And we consider that, and then that one of the independent variable was categorical, and then that categorical variable had two labels. So now what I'm going to do is I'm going to show you how do we do that if more than one variable are categorical, more than one independent variable are categorical, and that category may have more than two labels in it. Okay, so the method is exactly similar, just you will need one more plus there, and then the outcome will be more rows there. So let us see that. So I am pulling a support data set. You can download the support data from the Vanderbilt University Biostatistics dataset. Okay, you can search in the Google. So in the Google, you can search Vanderbilt Biostatistics dataset, and then the first link, if you click that, then you see the list of the data, and if you scroll down, then you see that support dataset. Okay, there is a support.xls. If you download this and then save it as support.csv file, okay, let us go to the what is that description, or here you can see that it says what are the variables and what types of variables are there. If it is a categorical variable, how many labels are there, and so on. Okay, for example, there is one column called age. Age is numerical value, it is continuous, and then death, and then sex will be categorical value with two labels, male and female, and DG group, DG class, all those kind of things are here. Okay, all those labels are here. See that? And if you want to see what that support data is, then this is the description of the data set there. The support data set is a random sample of 1,000 patients from phase 1 and 2 of support. Okay, study to understand prognosis, preference, outcomes, and risk of treatment. This data set is very good for learning how to fit highly nonlinear. So these are all the description you can read. Okay, so there are binary data set, there are ordinal data set, continuous data set, and so on. See the following references for more information about the support study, funded by, this is all these detailed information about that data. Okay guys, you see that level 1 means, so on the ordinal functional disability variable, if you look at the column of SFDM2, it has following labels. There is 1, 2, 3, 4, 5. These are the categorical variable, but it is saved as 1, 2, 3, 4, 5. So okay, be careful. These are the categorical variable. When you do the linear regression, you should write this as, save this as a factor. Okay. So 1 means patient live 2 months to be able to get 2 months interview, or and so on. You can read those. Now you see these are SPS, means variable name. SPS means support day 3 physiology score. APS means Apache 3 day 3 physiology score. So all these things are given here. You can look. Okay. Now what I want to do here though is I save this data set. Okay, I click this and then I save. Let me click it again. I saved the data set in my computer, and then again I open that data and then I save as .csv file. Okay, that's what I did. So that file is here. What is that support file? The support file is, let me go back to biostat argo data. Under the data, there is a support file there, support.csv. I saved it as a support.csv. Okay, .csv file. All right. Now I am going to read that file, that data set by R. I read it, and then I'm just printing the first 10 lines. Okay, and then you can see that how does that data set look like. There's so many columns there, right? You can see the structure and then see that. But anyway, the first column is age. The second column is death, dead or still alive. that way. Okay, the another column is sex, is male or female, hospital dead or not, is it dead by hospital, dead in the hospital or not. So all these things are given here. Okay, that's the data set. All right, so structure of A, you can see which data is factor, which data is numerical, and so on. You see that there are 1000 observations, 1000 rows, and 35 columns. So the age is the numerical value. Death is integer, but it is categorical because there are like death is either dead or alive, right? So that is 1 and 0. And sex is, it is also factor variable. It has two levels, male and female. They denoted by 2 and 1. Female is 2, male is 1. They denoted by like that. Okay. But when we do in R, we will denote, we can denote by 2 and 1, no problem there. But we will do factor. Make sure that you save it as a factor variable. Okay. All right. And then the hospital date 0 and 1. So all these things you can see from here. But whenever you analyze using the linear regression model, if the column is factor, make sure that you save that as a factor, because the data is maybe stored or saved in differently. Okay, so you should make sure that they are saved as a factor variable. What I'm going to do first is I want to plot the age versus the total cost of the hospitalization. Okay, age versus the total cost of the hospitalization. I'm using the red color for that. I'm plotting the scatter plot. Okay, and x-axis, along x-axis it will be age, along y-axis it will be cost, but I am doing for male and female differently like we did in the previous one. Okay, you see that I'm doing the male first, sex equals to male first. Okay, and then that's what you will get. You see that these are the data. You see, whenever the age increases, okay, then does the total cost decrease or increase? We'll find out that it sounds like it is not very much significantly increase or decrease, but we cannot say for sure from the scatter plot only. Okay, this is for male because the first one is for male. Second is because it is under that plot, I'm just doing points because it is a scatter plot. So so age versus the total cost for the sex female. Okay, that's what we do. So if I run that, you will see the blue dot colors, and then I'm writing the legend as the first one is the male, the red one is the male, and then blue one is the female. Now what I'm going to do here is I'm going to do the linear regression for total cost versus the male age. Okay, and I will do the total cost versus the female age. Okay, so does increase in the age increases the cost linearly or not? That's what I'm going to test. But before we do the hypothesis testing, what I'm doing is I want to plot the line and then see that does the male has a higher cost or female has a higher cost and so on. Okay, that's what I'm doing here. I'm not printing any summary. So this is the line. You see that the line is almost a horizontal line. It looks like there is no such, but what you can say here is whenever age increase, then the total cost of the hospital stay is decreased a little bit. You see that? All right. And that is for male because that's the red line. Similarly, I want to draw the line for female. You see that? They are almost the same. So whenever the age is small, then the female has higher cost of hospital stays than male, right? But here when the age is more than 85 or 90 years age, then the male has more cost. Total cost of the male is more. It sounds like that, but we need to test statistically whether that is significant or not. The graphs tells us that, but we don't know for sure. Okay, so what I'm going to do here is I am doing the total cost y versus x1 plus x2. x1 is age, and then x2 is sex, all together. Okay, all together here. So if I do this and then run the summary, what do I get here is, look at this. This is the coefficient of age, okay, and this is the coefficient of sex male. Okay, because sex has two levels, male and female. So this is the coefficient of sex male. If you want to write the equation for this, so how would that look like? So the cost equals to, you can write that A, okay, so you can write A plus B1 x1 plus B2 x2, okay, that's what you can write. What does that mean? That means A is this number, right, minus, you can write minus, and then that times the age, age is a numerical variable, and then the another one is minus, you see that times the male, right, that times the male, so I don't need double negative, I need just that. Okay, so this is that cost equals to. Okay, well, how do we determine? Oh, by the way, look at the p-value. This is age is significant, but gender is not significant. So male is not entirely significantly different from female. That's what it means, right? Because there were two of those. There were male and female. But for male, we got the p-value greater than alpha, meaning that there is no significant difference of the total cost. For all ages, there is no significance of the total cost between male and female. That's what we see, right? Because the dependence on the male and female is not significantly different. Okay, or you can say that the total cost is not significantly depend on the male or female. Okay, not dependent on more male or female. It is almost the similar. That's what it means. Okay, but how do we interpret that? So this is basically, these two are the mainly important thing. This is just the constant value, right? But this is the average cost of for all ages, okay, and for all genders, kind of. You see that without age or without gender, that is the average cost, okay, of the hospital stays. Now this is significant, the age is significant. I want to interpret this result. How do I say that? Is if so the total cost of the hospital stay will decrease by 436 if the age is increased by 1. That means that older people will have less cost of hospitalization. Okay, that's what it means, right? If you increase the age by 1 year, then the total decrease is $436.95 of the hospital stay is that. Okay, similarly, if this was significant, how would you interpret this? That means male have lower hospital stay cost than female by $3891.95. That's what you would say. Male have lower, because this is a categorical variable, right? So you compare with the one that is missing. So male has lower hospital stay cost than female. The average hospital stay cost of male is lower by $38.91 compared to the female. That's what you say. Okay, guys. So here, although you see that R squared is very small, just 2%, right? So the data doesn't fit to the line that much, but the p-value is significant. Okay, that means that the linear regression is significant. Now, what I got here is, since the sex is not significant, what I'm going to do here is I am removing this. Okay, I'm removing this and I'm just doing the simple linear regression here. If I do that, what do you get? You get that this is significant again, with for every 1 year increase in the age, the total cost of the hospital stay is to go down by $432.69. And but again, the thing is here, the R square value or R value are very, very small. Okay, so the fit is not very good. You can see from here, right? Because some of the data are so high, some of the data are low. So it sounds like no correlation, kind of. Okay, but since the data set is big and you see that the line is capturing the trend of the data, it looks like whenever age increase, the cost is decreasing, right? So the next thing what we want to do is we want to see if the cost is differed by, so we see that cost doesn't depend on the gender, right? But does the cost of the hospital stay depends on linearly with the race or not? So what I'm going to do is, first of all, I want to see the plot. Okay, so what I'm going to do is x value will be the y. So I'm doing the race white. Okay, so see, the x-axis is age, y-axis is total cost, but this is for the white people only, and denoted by green dots. And the next one is the Hispanic, is denoted by black dot. Another is the black African American, that is I am denoting by the orange color, orange circles, right, and so on. So this is what I am doing. So let us look at that. This is for white male only. Okay, the black one is for Hispanic, the orange one is for the African American, and then another one is the, what is the other? Other is the other. So the brown color is the other type of people. Okay, other skin color. Okay, now I'm writing the legend, and then if you look at that, the white, Hispanic, black, and other. Now I want to draw the regression line for each of those colors there. Okay, so I'm doing, for the first one, I'm doing the total cost wiggle. I'm doing the, to draw the regression line, you need to do the regression, you need to run the regression analysis for simple linear regression, just one x, one y. That's what I'm doing here for the y. So total cost versus age. Okay, that's what you do. If you do that and run that, this is the line, the green line. It sounds like it is decreasing also. For the Hispanic, this is another line, almost same, right? Sounds like there is no significant difference in the dependence, right? And then the other one is a little bit different, right? And that's the other one. So you see that almost all of them are similar, right? So if you do the total cost versus age with the different races, I'm doing all together at the same time. You see that? Age plus sex plus race. If I do that, what do you get? And then do the summary, you see that? Which one is significant? It sounds like only the age is significant, right? You see that? Only the age is significant. That has the p. You see the stars here? That has p-value less than alpha. But all other, the sex and the race is not significant, meaning that the total cost does not depend linearly on the gender or race. That's what we see. Okay. All right. So what I'm going to do is I want to check, because I just did age only. I did age and sex, but I haven't done the dependence on sex and race, right? I have to check if the total cost depends on just sex and race only. If I do that, so it sounds like p-value is greater than alpha. So no, it does not depend, right? Here the p-value was significant, but here if you take the sex and race only, then the p-value is not significant. Okay, so what we can say here, by the way, see, r square is even smaller, so we don't actually say that this data is not fitting to the line, because the data is so scattered there. Okay, so overall p-value is less than alpha on this one. Okay, this one, when we do the multiple linear regression. So the linear dependence is significant. It appears that age is the only variable causing the significant change in the total cost. That's what we can say. So this is the end of multiple linear regression. Okay guys, thank you.